Hello and welcome to the IC walkthrough for Down Under CTF 2024. So this is a beginner or easy hardware challenge where you had to read out an I2C EEPROM that was connected to your target. So we're gonna start by looking at the schematic here. So this was given to you in the handout, and I just want to do a quick walkthrough of all the components and how they're interconnected first. So first we have this part on the left. This is U. This is the Raspberry Pi Pico equivalent that your code will be running on. And yeah, so you can see a lot of these pins are no connect. That's what this little cross means. Then on the left here we've got a bunch of challenge management stuff. So this is you can just ignore this. You can see these will connect over to this part, the challenge ID chip. Just ignore that. It's not part of the challenge. And then we see over here IO4 and 5, they're labeled SDA and SCL. These stand for serial data and serial clock. We'll get to where they connect next. So over here we have this other chip which has this part number. We'll look that up in a second. But we can see it also takes in these SDA and SCL signals, as you can see by the labels here, and these wires as well. They go into these pins. So just a quick bit on reading schematics. So you've got these green wires, or they're wires essentially. They connect between things, but you see how there's this big disconnect. That's because these are labeled. We know that labeled things usually mean the same thing, like they connect them to each other. So if we draw a line between them, this schematic would be equivalent, something like that. But just to tidy up the schematic a bit, we omit those wires and we label them instead. And so we've got 3.3 volts here. That's what 3v3 means. 3.3 volts is just a standard way of notating it. Then we've got this write project jumper, so this is just so that people can't write to the EEPROMs and we have to keep reflashing them as people remove the flags. And then we've got, this chip. So this is a I2C EEPROM chip. We can find it by Googling this datasheet, or for the datasheet for this chip, which we have here. It says it's a 1 kilobit or 2 kilobit serial I2C bus EEPROM. So EEPROM stands for electronically erasable programmable read-only memory. So this is kind of like your hard drive, except you would only read or write from it a few times, or rather write to it a few times, but you'd read it a lot. So this is usually what we'd use for storing stuff like configuration for a program running on our microcontroller, where it doesn't change a lot, but we might want to change it a few times, when we're setting it up, or we might code in a serial number into it and just once and never erase it. But it's just a nice way of very cheap and small storage. So we can see it's got I2C interface, compatible with 100 kilohertz and 400 kilohertz modes. We're only going to really use it in the 100 kilohertz mode. We're not reading that fast. We're just reading once. And yeah, we can see it's either 1 kilobit or 2 kilobit. The way you actually determine this, if you read way further down the datasheet, is by this 01 means 1 kilobit and this 02 means 2 kilobit. In our schematic, we've got the 02 variation, so this means we've got 2 kilobits of data. And so now, next thing is, how do we read and write from this? So we've worked out that this is an EEPROM. It stores some data. We're going to assume it stores the flag, considering that's like the only thing on the schematic other than this challenge ID chip, which again, ignore it. Yes, it stores some data on the, just a quick thing I want to mention as well, this capacitor, so this is the capacitor on the left here. Oh, why isn't it zooming in? We'll zoom in. This is a capacitor over on the right here. This is for decoupling. So this means if other devices that are connected to this 3.3 volt start drawing too much current, the the voltage level might drop a little bit. So this capacitor, we place it near this pin. That's what this place near P8 means. Place near the where we want 3.3 volts. That's just so that we maintain a stable 3.3 volts next to this chip, as like there's lots and lots of little current fluctuations, voltage fluctuations going on. Yeah, that's just an aside. That's why this is here. But we can't really do much with it. So yeah, we'll move on to how do we read this EEPROM. So we see we've got I2C connected. So that's SDA SCL again. So we can check the Raspberry Pi datasheet or the RP2040 datasheet for the connector here, or for your runner. It's based on the Raspberry Pi Pico, which in turn is based on the RP2040, a chip by the Raspberry Pi Foundation. And so if we flip all the way to GPIO functions, we can work out that GPIO pins 4 and 5, if we come back to function 3 here, we can see it's I2C0 SDA and I2C0 SCL, which is exactly how we have it connected here. So that's good. We can use the hardware I2C peripheral inside this chip, which is good for us. Makes our lives so much easier. And then, yeah, next thing is reading the data out of this EEPROM. So if we flip over to like read or write operations, we'll start here. So there are some timing diagrams here that are nice and useful. So if we want to write a byte, we will have to send a device select, an address that we're going to write from, or write to, and then some data that we want to write. But we actually want to read. So we'll look here again. This only has, here we go, sequential random read. We want to select a device, then we want to write the address of it, of the device, and then we want to start another transaction, and then we'll run a select, and then we'll read the data out. And then we can do that as many times as we want until we get to the EEPROM, and then we send a stop bit. So, how do we do this? Firstly, what is dev select? What is this? So this is a I2C byte. So it's a byte in I2C that tells us which device we're talking to. So if we actually flip over to this section of the datasheet, the main thing in that byte is an address. So most I2C drivers implement this for you. The Raspberry Pi one's no exception. But all we need to know is the address that comes out of it. So we can see how the different bits are selected. So we start with 1010, and then we use E2, E1, E0. These are signal names, like it says up here, I think. Yeah, these must be always set to logic 0 for any operation. Oh, that's in a different package. Ignore that. But if we look over here, we can see we have E0, E1, E2. We can see these are, if we follow these lines, they're tied to 3.3 volts, which means they're a logical 1. So that means our address is going to look like 10101111. And we've also got this bit 0, which is read not write. So if it's a 1, we're reading. If it's a 0, we're writing. But our I2C driver implements this for us in the RP2040. So we're just going to ignore that. And we're going to consider our address as 10101111, or in hex this is 0x57. So now that we know the address and roughly how to read and write, let's get writing some actual code. So for this, we're going to use the Raspberry Pi Pico SDK. Our hardware infrastructure here allows you to use RPSDK, Pico, or RPRS, Arduino Pico that is, or RPRS. You could really write this in assembly if you wanted to. I don't see why you would, but all we're looking for is an ELF file that will run on the RP2040, and then you get to upload that, submit that. That's how this works. So the other things I want to highlight from here are you get access, you get to talk to your code that runs. So we have a 115/200 baud UART connection. So this is just like a serial, a way you can talk serial back to your code that you're running. This is consistent for all 4 challenges that we set up, and they all talk on IO0 and 1, which is why you'll notice from the schematic they're omitted, because this actually happens internally inside our clustering infrastructure. And where were we? Here. Yeah, so you can talk on UART back to your device. So we'll look at how to use the Raspberry Pi SDK now. So here you can see, you can read all this if you want to, but the main thing is, here's quick start. You want to install a bunch of these libraries on your system. So that's the ARM no EABI version of GCC. You want libnewlib compiled for ARM no EBI, and you want standard C++ compiled for no ABI with newlib. And then yeah, so here we're just gonna pick one of these. There are multiple ways to set up the Pi SDK, but the fastest one I find is using the git clone it, copy this file across, set this environment variable, and then just use a CMake file. So I've set up a project here where we've already got the code here as well, but I've cloned in the Pico SDK directory. You can see that here. This is just a direct one-to-one clone of this Git repository. And then we've got, I haven't copied this file over, I'll show you why in a second, but then we'll set this Pico SDK environment variable, so that is to this Pico SDK directory. And then we'll set up a CMakes list file, which I've already done. Essentially, what we're doing here is we are setting our CMake version. We're including that Pico SDK import file. Usually you wouldn't have the Pico SDK cloned in the same project directory. Usually you'd have it globally somewhere, which is why it says to just copy this file over. But in this case, I've just pathed to it. Then we can set up a project. We initialize the Pico SDK, and then we get to add some stuff for how our code should compile. So we're going to create an executable called solver with our source code solver.c, which we'll get to in a second. And then we're going to link in everything that we need for that. So we need the Pico standard library, and we also need access to the hardware I2C peripheral. And then we'll create a bunch of extra files. We don't actually need these, but this is like how default the Pico SDK wants us to do it. And then we'll turn off using standard I/O and USB because our infrastructure doesn't use USB for serial. That's one of the common pitfalls I saw people running into with the hardware infrastructure, is that they're using USB for serial rather than the UART. So we also enable the UART over here. And yeah, so that's that. Now back to our solver.c file. This is how we're going to solve the challenge. So we're going to firstly init standard I/O. The Pico SDK is really nice to us. We don't have to do all the UART configuration, anything like that. That's all set up here when we set up standard I/O in that CMake file. All happens in this one function. So we're just going to print a little message out. That's what puts means, put string. Then we're going to initialize the I2C peripheral. So we're going to use I2C 0, and we're going to clock it at 10 or 100 kilohertz. And then we're going to just configure those GPIO pins to use their alternate function of SDA and SCL, or be connected to I2C. So if we check the datasheet again, we've got pin 4, it's function 3, that's what this macro expands to, GPIO func I2. It's pretty consistent. You can see if we look down this entire F3 column, it's just I2C connections. And then, yeah, we'll do that for pins 4 and 5, and then we'll also set pull-ups on the GPIO pins as well, because if you actually noticed in the schematic, we didn't have pull-up resistors on here. So you've got to do those internally in the connector or in the RP2040, just so you can talk to this nicely. And then yeah, we'll start implementing what we did in what we saw in the datasheet. So we will start by setting up this buffer. So this will be the data that we send. So we just want to start reading. So this is the byte address. The dev select is handled, like I said before, by the SDK driver. So we've got the byte address, which we want to start reading from. So that'll be 0x00. So that's just the first byte. We want to read the first byte. Sounds like a reasonable guess for where the flag will be. Yes, we'll transmit over, this will expand to 1 byte onto address 0x57, which again we found in the datasheet a bit ago. And yeah, so this 0x57 along with this read-write bit will be managed by calling read or write blocking here on I2C0 with 0x57. And then this true here means don't send a stop bit, because you see we want to send a start bit, but we don't want a stop bit until the very end. So we're not going to send a stop bit. So then we'll print a message so that we can check that our code's going good, that we sent the address. And then we'll read. So again, we'll read from that address and we'll read into this variable EEPROM data 256. So this is a uint8t, or like 1 byte each element array of 256, so of size 256, so that's 256 bytes. And then yeah, this will expand again to 256 bytes of data, and this time we do want to send the stop bit, like we can see at the bottom of this data sheet here, or this page in the data sheet. And then after that, we'll just print the data out, chuck a few new lines in there so everything looks nice, and we'll print out the EEPROM data. Here we're assuming that the data in here is a string. I know it is. I wrote the challenge, but you could just as easily, hex dump the data, output in binary if you really want to, base64 encode it. You could do anything you really want to. But yeah, I just know it's an ASCII string, so we're just going to print with the %s format specifier. And so now that we've done that, quit. Okay. So then we will we'll make a new directory for build, which I've already done, and we can cmake ... so we'll compile for that previous, with all the code in the previous directory, and then we'll just make it. So here we've got this solver now, so if we list the files in here, we see we have solver.elf. So we can then come here to this website, the hardware infrastructure submission page. We can grab that elf file and we can upload it, and then we can run it. So our code will get queued for a second, it'll take a bit to run, and then we'll be able to get logs. So the logs will be, if we download these, and then I go ahead and I cat them for you. So if we actually, that messed up the CSS a bit. Okay, so if we just grab this run, cat downloads A6, A5, that one, we can see the flag here, but there's also all this garbage P1 stuff. That's just some framing data. We can actually use there is a tool linked up here where you can compile this tool and you can actually view the data that went through in real time. So I've already compiled it. Let's see, hardware log viewer, and we'll just pass through that file, and here we go. So you can see we get the I2C EEPROM dumper. We read, or we sent our address. We are going to send the address. We sent the address, we read the data back, and then here's the data that was in the EEPROM. So blah, 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 here's your flag. And if you handed this flag in, that would be correct. And so that's how you solve the IAC challenge, and a little bit of a walkthrough on how to read schematics, how this EEPROM works, and how the hardware infrastructure worked in general.